Time travel isn't just for the big screen. What if the universe itself is hinting at its possibility? For generations, we've dismissed it as pure fantasy. But groundbreaking physics and mind-bending theories are suggesting otherwise. Today, we're ripping through the misconceptions to uncover exactly why hopping through centuries isn't just a dream, but a mind-blowing potential reality. Get ready to see time itself in a whole new light. Einstein's special theory of relativity, a cornerstone of modern physics, postulates that time is not absolute, but relative to an observer's motion. This phenomenon, known as time dilation, means that time passes more slowly for objects moving at high speeds relative to a stationary observer. Experiments with atomic clocks on high-speed aircraft have repeatedly confirmed this effect, demonstrating that clocks moving faster record slightly less elapsed time. Thus, traveling into the future, relative to a less mobile observer, is a scientifically proven concept achievable by high-speed motion. Expanding on this, Einstein's general theory of relativity further demonstrates that strong gravitational fields also cause time dilation. Near massive objects, such as planets or black holes, time itself slows down for observers within that field, compared to those in weaker gravitational regions. This gravitational time dilation is accounted for in the precise functioning of GPS satellites, which must adjust for Earth's gravity to maintain accurate positioning. Therefore, spending time in a stronger gravitational field would result in experiencing less time than someone in a weaker field, effectively moving into their future. Theoretical constructs known as wormholes or Einstein-Rosen bridges represent another potential pathway for time travel by offering shortcuts through space-time. These are hypothetical tunnels that could connect two distinct points in space and time, significantly reducing the travel time between them. While currently purely theoretical, the mathematical framework of general relativity does not explicitly forbid their existence, suggesting they could theoretically allow for rapid transit across vast cosmic distances. For a wormhole to be traversable and stable, however, it would necessitate the presence of exotic matter with negative energy density. This hypothetical matter would exert an outward gravitational push, preventing the wormhole from collapsing upon itself and keeping its throat open. Although the existence of such exotic matter has not yet been confirmed, some quantum phenomena, like the Casimir effect, hint at the possibility of localized negative energy densities under specific conditions. The concept of closed time-like curves, or CTCs, emerges from certain solutions to Einstein's field equations, suggesting paths in spacetime that loop back to their starting point. Traversing a CTC would allow an object to return to an earlier point in its own history, enabling travel to the past. Various theoretical scenarios, such as rapidly rotating black holes or specific spacetime geometries, could potentially generate such time-bending paths. Physicist Kurt Gödel, a close associate of Albert Einstein, famously discovered a solution to the equations of general relativity in 1949 that described a rotating universe where CTCs are inherently possible. In Gödel's model, an observer could, in theory, travel into the past by moving along a sufficiently long circular path. While Gödel's universe does not precisely match our observed universe, his work demonstrated that time travel to the past is not fundamentally forbidden by the laws of general relativity itself. Another theoretical mechanism for creating CTCs is the Tipler cylinder, proposed by physicist Frank Tipler in 1974. This hypothetical object involves an infinitely long, massive cylinder rotating at immense speeds. According to Tipler's calculations, an object circling such a cylinder could theoretically follow a path that leads it back in time. However, the requirement for infinite length and mass makes the Tipler cylinder an impractical, purely theoretical construct, serving more as a thought experiment. While not direct time travel, the theoretical Alcubierre drive proposes a method for faster-than-light travel by distorting spacetime, rather than moving through it. This concept involves creating a warp bubble around a spacecraft, contracting space in front of it, and expanding space behind it, allowing for apparent superluminal speeds without violating local light speed limits. The block universe theory, a philosophical implication derived from general relativity, suggests that all moments in time, past, present, and future, exist simultaneously and are equally real. In this view, time is not a flowing river, but rather a static dimension analogous to space, implying that our perception of time passing is an illusion. If the block universe accurately describes reality, then traveling through time might be conceptually akin to moving through a spatial dimension, making past or future accessible in a different sense. The scientific exploration into the possibility of time travel continues to push the boundaries of our understanding of physics. While immense practical engineering challenges and the need for exotic matter persist, the mathematical consistency of concepts like time dilation, wormholes, and closed time-like curves within Einstein's theories keeps time travel within the realm of scientific possibility. These theoretical frameworks highlight that time, as we perceive it, may be far more flexible and complex than once imagined, inviting ongoing research. Thanks for watching. Please subscribe to our channel.